In this video, I will illustrate how a simple EM algorithm to infer allele frequencies can be implemented in R. I will begin by describing the model briefly. The model is also shown on the right as a DAG. The general aim is to infer the allele frequency f at a particular locus, as well as the sequencing error rate epsilon from some sequencing data of n individuals. We're going to denote the data of individual I by di. Let us make a bunch of assumptions. First, the locus concerned shall be biallelic. That is, it only contains two alleles, the A allele, the ancestral allele, and the D allele, the derived allele. The genotypes G shall denote the number of derived alleles. That is, a genotype of 0 would correspond to a genotype consisting of only ancestral alleles, that is, homozygous ancestral. The genotype 1 would be the heterozygous genotype, and the genotype 2 the homozygous derived genotype. We're going to make further the assumption that the genotypes among the individuals shall be distributed according to Hardy-Weinberg equilibrium, that is, binomially distributed. The probability of having an ancestral homozygous genotype is then 1 minus f squared. The probability of a heterozygous genotype 2f 1 minus f, and the probability of a homozygous derived genotype f squared. The data di of an individual shall further consist of mi independent reads. Some of those reads, MIA, will carry the ancestral allele, and MID of those will carry the derived allele. The probability of observing this set of reads di, given a genotype in epsilon, shall further be the product of observing a particular base of each read, given a genotype in epsilon. That is, we make the assumption that given a genotype and sequencing error rates, all the reads of an individual are independent. The probability of a particular base given a genotype in epsilon depends on the combination of genotype and observed base Bij. If the genotype is homozygous ancestral and an ancestral allele is red, then that means there is no sequencing error, and that happens with probability 1 minus epsilon. The same applies for the case in which the genotype is 2, that is homozygous derived, and a derived allele was actually red. The opposite case would be a genotype 0, that is homozygous ancestral, but the observed allele would actually correspond to a derived allele. That happens with probability epsilon, that is, a sequencing error occurred. The same applies to the case of genotype 2, homozygous derived, and an ancestral allele that was observed. At heterozygous genotype, the probability of observing either allele is simply 1/2. The goal is now to find the maximum likelihood estimator of our two parameters f and epsilon. We're going to treat here the genotypes Gi as latent variables. That is, we are not really interested in them and would like to integrate them out. For this model, the likelihood of f and epsilon, that is the probability of all the sequencing data of all individuals given f and epsilon, is given by the product across all individuals, which are independent if we condition on f and epsilon. And then for each individual, we have the sum across all genotypes of the probability of the data given that particular genotype in epsilon, weighted by the probability of that genotype given f. In order to find the maximum likelihood estimates under this model, we have to resort to an EM algorithm. In order to develop an EM algorithm, we have to derive or write down the complete data likelihood, LCF of epsilon. To do so, we're going to treat the hidden genotypes, the latent variable G, as known data. That is, we're interested in building the probability of the data as well as the genotypes given f and epsilon. The complete data likelihood is of a simpler form. It is simply the product across all individuals of the probability of the data given the now known genotype Gi of that individual times the probability of that genotype given f. We can take the log of that likelihood to define the log complete data likelihood LCF of epsilon, and that just becomes the sum across individuals of the log of the probability of the data given the genotype of that individual in epsilon plus the log of the probability of the genotype given f. The E step of the EM algorithm then consists of building the so-called Q function. That is, the expectation of the complete data log likelihood, LCF of epsilon, given all the observed data, as well as some current estimates of f and epsilon divided by f prime and epsilon prime. That expectation consists of, for each individual, summing over all possible genotypes and weighting the complete data likelihood by some weights PGI. These weights themselves are obtained simply from the model using Bayes' formula. They consist of the probability of the data given a particular genotype times the probability of that genotype given F prime divided by the normalization across all possible genotypes. In the M step of the EM algorithm, the goal is then to find values for f and epsilon that maximize the Q function. We obtain solutions for f and epsilon by taking the derivative of the Q function in respect to these parameters and solving the system of equations for 0. The two functions that we obtain for this particular model here are shown on the right. Note that both of them only depend on the observed data, MID and MIA, as well as on the EM weights given by the equation on the left. Here, P1I, for instance, indicates the EM weight for genotype 1 for individual I. With all these derivations at hand, we can now set out to implement the EM algorithm. The first step of the EM algorithm consists of initializing all the parameters, in this case f and epsilon. Let us denote by t an index of the iteration. So we're going to first set t equal 1, and we're going to choose values f1 and epsilon 1. These are educated guesses of both of these parameters of the model. These initial estimates are then iteratively improved through both the E step and the M step. In the E step, we're going to use the current estimates of f and epsilon in order to calculate the EM weights. In the M step, we're going to then use the equations we obtained before to update the parameters f and epsilon using those weights. We're going to repeat the E and the M step iteratively until convergence is obtained. Key to the implementation of this algorithm is therefore to have a function that allows us to calculate the EM weights PGI under this model. On the right now I show you our code for exactly such a function. In this R code, I'll denote by A and D the number of ancestral and derived alleles, so those who correspond to MIA and MID in the mass, and by F and E the two parameters F and epsilon. We have to realize that the weights PGI have to be calculated for all combinations of genotypes and individuals. This is why this function returns a matrix with one row per individual and one column for each of the three genotypes. We can then fill in those weights for each genotype separately. The three equations for the three genotypes consist of two parts. The first part is the probability of the data given that particular genotype. So for the genotype of 0, that's for instance 1 minus the error rate at the power of the number of ancestral reads times the error rate at the power of derived alleles. And of a second part, which is the probability of the genotype given the allele frequency f. So for genotype 0, that would then be 1 minus f squared. You notice on the left that these weights have to be normalized by the sum across all possible genotypes. We obtain this in this function by dividing the weights by the sums of each row. With this function at hand, we can now implement the actual EM algorithm. We begin by preparing the storage so we can monitor how f and epsilon are changing through the iterations, as well as how the log likelihood, denoted here by Allele, is improving through the iterations. We also have to initialize the parameters. We provide to this function with f1 and e1 some first guesses of f and epsilon, and we store them at the first entry in the corresponding vectors. We then also calculate the log likelihood at this first iteration t equal 1. We then are going to iteratively improve our estimates at f and epsilon. This is done within the for loop, and within the for loop we have these two steps, the E step and the M step. In E step we have to calculate the EM weights, PG, and for those we need the function that we just defined before. In the M step we will then update both f and epsilon using the equations shown on the left. Note here that both A and D, the number of observed alternative and derived alleles for each individual, is given as vectors, and PG as a matrix for each individual. Note also that our indexes always start at 1. So rather than having the indexes used from 0 to 2 for the genotypes, we have to use them from 1 to 3. Once f and epsilon are updated, we will then calculate the log likelihood with those new estimates. We can then use the log likelihood to check whether we have reached some convergence. So basically, we're going to compare the log likelihood with these new parameters to the log likelihood we obtained with the previous parameters. If that improvement is smaller than some threshold delta Allele, or if we reach the maximum number of iterations allowed, we will actually return here the list of f epsilon as well as log likelihoods for this run. In order to verify the performance of our EM algorithm, we have to test this with simulations. So we first have to write functions that allow us to simulate data under this model. Simulating data on the model is always proceeding the same way. First, we have to choose values for the parameters of the model, in our case f and epsilon, and then we also have to choose the size of the data, that is the number of individuals n, as well as how many sequencing reads we should have for each individual. Here we can assume that the number of reads per individual is Poisson distributed with rate lambda m, which also corresponds to the average number of reads per individual. That's just a choice, and other choices to simulate the number of reads per individual might work equally well. Next, we're going to simulate the genotypes GI under Hardy-Weinberg. This is actually equivalent to binomial sampling, such that each genotype GI is a random draw from a binomial distribution with size 2 with probability f. Next, we're going to simulate the data DI. The data DI is simulated in 2 steps. First, we're going to simulate the number of reads mi per individual. As mentioned above, we can assume that these mi number of reads are Poisson distributed with rate lambda m. Once we know the number of reads mi per individual, we're going to draw how many of those are actually ancestral and derived. The number of ancestral reads for each individual are again binomially distributed with different probabilities depending on the genotype. So basically, we're going to have mi draws, and if the genotype is 0, the probability of obtaining an ancestral allele is 1 minus epsilon. If the genotype is 1, it's 1/2, and if it's 2, it's epsilon. The number of derived reads MID is then simply MI minus MIA. On the right, you can now see code in R that implements this procedure. This function takes as arguments f and epsilon, the number of individuals n, and the average number of reads per individual, lambda n. The function then proceeds just as laid out on the left. First, it simulates genotypes by drawing random numbers from a binomial distribution of size 2 with probability f. Next, for each individual, the number of reads are simulated by drawing a random number from a Poisson distribution with rate lambda n. For each individual, we then simulate the number of reads that have the ancestral base. This has to be done for each genotype separately. So for all individuals that have a genotype of 0, we draw a random number from a binomial distribution with probability 1 minus epsilon. For all individuals that have genotype 1, we draw a random number from a binomial distribution with probability 1/2. And finally, for all the individuals that have genotype 2, we draw a random number from a binomial distribution with probability epsilon. Finally, this function returns the data as a data frame, both by returning the number of ancestral alleles as well as the number of derived alleles, which is simply m minus a. Note that here, a and d are both vectors, so this data frame has the number of rows equal to the number of individuals. Let us now make use of this code to test our EM algorithm. For this, I now simulated data with a true allele frequency of 70% and a sequencing error rate of 5%. What you can see here on the left is a trace of an EM algorithm in the two-dimensional parameter space of f and epsilon. The black square indicates the first guess of the parameters, so that is the place at which the EM algorithm started. The EM algorithm then proceeded along this line with each dot representing one iteration. The final iteration is very close to the true value, which is marked with these dashed lines. On the right, we see the trace of this EM algorithm in terms of the log likelihood. Our initial guess had a log likelihood that was quite far away from the final log likelihood achieved by the EM algorithm. And as you can see, with every step, and with every iteration, the EM algorithm improved the log likelihood until it converged. I next ran the same EM algorithm on the same data, but for different starting locations. Each run is indicated in a different color. As you can see, most EM runs seem to converge to the same values of f and epsilon. One run, however, the yellow one, seems to converge to different values of f and epsilon. Interestingly, however, also this algorithm seems to find a solution for f and epsilon that has the same log likelihood as the other ones, as shown on the right. So how can it be that these different EM runs seem to find different solutions of f and epsilon, but that these solutions seem to be equally probable? It may help to understand what's going on by plotting the likelihood surface underneath these EM traces. The likelihood surface here is calculated using a grid search, so that's certainly not a good approach for finding maximum likelihood estimates, but it does help to understand what's going on. And the likelihood surface indeed confirms that this problem has two solutions, and it shows that each EM run is simply climbing the likelihood surface to find whatever peak is reachable from the starting location. To see that this model has indeed two solutions, consider a case in which the data consists mostly of derived alleles for most individuals. Such data can be observed under two different scenarios. One is, we have a high allele frequency, such that most individuals have derived genotypes, either heterozygous or derived homozygous, and then a low sequencing error rate, such that most of the reads observed for those individuals indeed show the derived allele. However, a lot of derived alleles might also be observed if the genotypes are actually mostly ancestral, that is, we have a low allele frequency and most of the genotypes are ancestral homozygous. However, the sequencing error rate is very, very high, such that most of the reads observed are still derived even if the genotypes are actually ancestral homozygous. From a mathematical point of view, the reason that there are two solutions is simply that the probability of the data given f and epsilon is actually the same as the probability of the data given 1 minus f and 1 minus epsilon. To convince yourself that this is true, simply plug in 1 minus f instead of f and 1 minus epsilon instead of epsilon into the equations a few slides back. The solution with a very high sequencing error rate may not be very realistic, illustrating that external or a priori information on parameters is actually very important in inference. While Bayesian statistics offers a very natural way of including such information, the kind of preferred P could be found in this model here also by maximizing under some constraints. So for instance, saying that we are only interested in solutions for which the sequencing error rate is less than 0.5. But this also illustrates a more general issue with the EM algorithm. The EM algorithm is an algorithm that is just climbing the nearest peak. Only by running the EM algorithm from many different starting locations do we actually have a chance to figure out whether the solution we found is the global maximum or instead just a local peak.